Hey guys, so we're going to go over day 8 notes today, double replacement. Okay, so double replacement, we have ions from two ionic compounds switch places. Okay, so looking at your general form, we're going to have an AB compound plus CD compound, which yields CD plus AD. Okay, so there's two ways you could look at this replacement. One of those ways is cations are going to switch places. So you can consider it that A and C are going to switch places. Okay, since A and C switch places, C is now going to be with B. Okay, and then A is now going to be with D. Okay, so that's one way of looking at it. Your cations are switching places. Or another way you can look at it is that your inner ions are going to combine and then your outer ions are going to combine. So when we say inner ions, that's going to be your ions closest to the plus sign. So that's going to be B and C, so right there. And then your outer ions, A and D, are going to combine. Okay, so that's the two ways that you can think of double replacement. And then, of course, your identifying feature is that two compounds, you're going to have two compounds on each side of the equation, which we can see in your general form right here. One compound, two compound. One compound, two compound. Okay, so two compounds on both sides of the equation. Your analogy is that you have two couples that are dancing, and then those couples switch partners. Okay, so again, you can think of it as A and C are going to switch places. Okay, or you can think of it as your inner ions are going to combine, and your outer ions are going to combine. Okay, so as far as dancing partners go, okay, you can see that the guy with the glasses and the guy with the cowlick are the ones that switch places. Okay, or again, C and B are now going to be dancing partners, and then A and D are going to be dancing partners. Okay, so if you look at it chemically, I like to actually write down the path of where they're going. Okay, so we have iron chloride plus sodium carbonate. So again, your inner ions are the ones closest to your plus sign. Okay, so sodium is now going to bond with chlorine, and then iron is now going to bond with carbonate, okay, which we see here. Sodium and chloride, and then iron and carbonate, Okay, so you have a table right here. We're going to skip over that really quick and go to the next page. You have two terms, soluble and insoluble. Okay, some of you guys should already know this. Soluble means that it will dissolve or it can dissolve. Okay, and we label these compounds as aqueous. Okay, because they can dissolve in water. And that is the definition of aqueous. Aqueous is something that is dissolved in water. Okay, and then insoluble means that it cannot be dissolved. Okay, so if it can't dissolve in water, then it's going to stay a liquid. So we're going to label our insoluble compounds as a solid. Okay, so now how do you determine if you have a soluble compound versus an insoluble compound? Well, that's when we refer to, that's when we refer to this table right here. Okay, so you are going to use this table to determine whether or not you have a soluble compound or an insoluble compound. Okay, which you can also find on the back of your periodic table. If I actually show it to you guys. Okay, so the back of your periodic table. Okay, remember that your activity series is for Rule 1. Okay, all for Rule 1. Or I'm sorry, single replacement rules. Okay, one more time. Activity series is for single replacement, And then double replacement is going to be for this one right here, solubility chart. Your solubility chart is for double replacement, and then again your activity series is for single replacement. Okay, so let's go ahead and take a look at this solubility chart and how do we use it. So we have a few examples in our notes, okay, which I've actually already done. Hopefully you guys can't see my answers. Okay, so if we have strontium nitrate as our first example, okay, to determine whether or not this compound is soluble, you are only going to use your negative ion. Okay, remember that when we write compounds, your first ion is always going to be positive, and then your second ion is always going to be negative. So in this case, we're always going to be looking at that second ion. Okay, so in this case, it's nitrate, NO3. So we're going to look at our table. NO3 is right here. So NO3 tells us, or our table tells us, NO3 is a soluble compound. Okay, and it has no exceptions, so it's always going to be soluble. Okay, so the next one we have silver and hydroxide. Remember, we're only looking at the negative ion, so hydroxide. So if we look hydroxide on our solubility chart, hydroxide is all the way at the bottom. Okay, and be careful, we have some exceptions this time. Okay, so we are attached to silver, so is silver any one of these exceptions? Okay, and your answer should be no. Silver is not any of these exceptions. Now be careful, an alkali metal are group 1 metals. So on the front of your periodic table, your group 1 metals are these right here. Okay, all these group 1 elements. Those are alkali metals. Okay, so let's go back to what we were doing. Okay, silver, hydroxide. Silver is not one of these exceptions, so hydroxide would be insoluble. Okay, let's take a look at the next one. We have lead and chloride, or chlorine. So lead, chloride. So let's take a look at chlorine. So chlorine is right here on our solubility chart. So is chlorine attached to one of these three? Silver, lead, and mercury. It is. Lead is actually an exception. So that would mean chlorine is no longer soluble, but insoluble. Okay, all because we had that exception. Okay. Just because lead was attached to chlorine, it would make this chlorine insoluble. Okay. And then lastly, our last example, we have sodium phosphate. So phosphate is right here on our solubility chart. And do we have an exception? It looks like we do have an exception, because sodium is actually an alkali metal. So that means that it would actually be soluble. Okay, so though that compound would actually be soluble. And I just realized I forgot to state what they are in the parentheses. So remember that if it's soluble, we are going to refer to it as, where is it? Okay, so if it's soluble, we're going to refer to it as aqueous. If it's insoluble, we're going to refer to it as a solid. Okay, so this is soluble. So that's going to be AQ. This is insoluble, so that's going to be a solid, another solid, and AQ for the last one, okay, because it's soluble. Okay? Alright, so moving on with the notes. Okay, so I kind of can't cover that. Okay, so a precipitate is a solid that forms when two solutions are mixed. Okay, the key word here is solid. So you know that a precipitate is a solid. So looking at this formula or this chemical equation, well, are any of these a solid compound? Your answer is yes. This compound right here is a solid, while all the others are aqueous compounds. So you know that, hey, this one right here is your precipitate. If you remember, this was actually one of your bonus questions from your quiz. We asked you, based on the following equation, which compound is your precipitate, and it would be the solid compound. Okay, so tips for double replacement reactions. Remember, do not use your activity series. Okay, determine if a precipitate will form. If a precipitate will be an insoluble product, and it should be marked as a solid. If a precipitate forms, then a reaction occurs. If a precipitate does not form, then no visible reaction will occur. Okay, and then your general formula, again, AB plus CD yields CB plus AD. And then the positive ions will always switch places. Okay, and then remember that your positive ions are also going to be the ones that go first. Okay, so let's go ahead and take a look at our sample problems. Give me just a second. I actually messed up my sample problem, so I'm going to have to grab a new packet to work off of. Okay, so, all right. So these are our examples right here. So our first step is to predict our products. Okay, so remember your inner ions are going to create a compound, and then your outer ions are going to create a compound. Or you can think of it as your cations are going to switch places. But I actually prefer using the inner and outer method just so I can see where everything is going. Okay, so copper was first. So copper is now with PO4. So CuPO4. Okay, plus I'm going to leave some space because I have to determine if it's aqueous or a solid. I'm going to leave some space there. Okay, and then our next compound would be sodium and chloride. Okay, sodium and chloride. Remember, positive always goes first. Okay, so let's go ahead and take a look at our solubility chart. Okay, so we have copper phosphate and sodium chloride. Copper phosphate, remember we're looking at our anion or our negative ion. So PO4 is right here, and it would be insoluble because copper is not an exception. Okay, so this would actually be insoluble, so it would be a solid. Okay, and then sodium chloride. Sodium chloride, we are looking right here. We're looking at chloride or chlorine. Okay, and sodium is not one of the exceptions, so it would stay soluble. Okay, so soluble would mean that we have an aqueous compound. Okay, now remember, if you have a solid compound, or if you have a precipitate in your reaction, you do have a reaction. From this step, you would go ahead and balance your equation, but I'm going to be honest with you, this equation is kind of difficult to balance, and it's kind of confusing, so we're not going to balance this first one. Okay, let's go ahead and take a look at our second problem. We have NaNO3 plus potassium chloride. Okay, so remember your inner ions are going to create a compound, and then your outer ions are going to create a compound. Okay, so we have sodium is now with chlorine, so NaCl, and then we have potassium nitrate. So potassium NO3. Okay, so sodium chloride, again, we just did that. It's an aqueous solution because remember, chlorine is considered soluble and sodium is not one of those exceptions. So AQ. And if you didn't know this already, but sodium chloride is salt. If you've ever put salt in a cup of water, does salt dissolve? Yes, it does. Okay, that's just some side information. And then let's take a look at our other compound. We have potassium nitrate. So nitrate is here on our solubility chart, and it is considered soluble. So because it's soluble, we are going to list it as aqueous. Now, taking a look at our products, remember what we said. In a double replacement reaction, you have to have a precipitate form. If no precipitate forms, then you have no visible reaction. Okay, you have no reaction. All right, so let's go ahead and move on to the next one then. Okay, so we have potassium hydroxide and iron nitrate. Okay, inner ions are going to pair up, and then outer ions are going to pair up. So we have potassium, so K, then NO3, and we have iron, FeOH. Okay, so potassium nitrate, let's take a look. On our solubility chart, nitrate is right here. It doesn't matter what it's bonded to, it will always be soluble. So I'm going to have an aqueous compound then. Okay, and let's take a look at iron hydroxide. So hydroxide is at the bottom of our solubility chart, and iron is not one of those exceptions. So it is going to stay insoluble. Okay, so again, we have a precipitate, so that means we have a reaction. Okay, because we have a reaction, we're going to need to balance our equation. And I'm going to be honest, I haven't been writing my compounds correctly. Okay, potassium has a positive 1 charge, nitrate has a negative 1 charge. Okay, crisscross our charges, well, they're actually going to cancel each other out, so I don't have any charges. For this one, iron is a positive 3 and hydroxide is a negative 1. Well, how do you know that iron is a positive 3? Well, remember, our subscripts tell us what our charge is. Okay, so if nitrate has a subscript of 3, then that means iron's charge is a 3. So crisscross your charges, this should be FeOH with a subscript of 3. Okay, so let's balance our equation. We have 1 potassium here and 1 potassium here. Okay, hydroxide. We only have 1 hydroxide on our reactant side, but we have 3 hydroxides on our product side. So that means we're going to have to add a coefficient of 3 here. Because we put that 3 there, it changes the number of potassiums we have. Okay, so that means on my product side, this has to also have a coefficient of 3. Okay, so because I put that 3 there, it changes the number of nitrates I have. I now have 3 nitrates on my product side. But if you take a look at your reactant side, I actually have 3 here also. Okay, so nitrate is actually balanced. Okay, and I believe the last thing we have to look at would be iron. Iron, we have 1 iron here, and iron on this side, we also have 1. So our equation is now balanced. Okay, and then the last equation that we have for our notes today, we have calcium chloride and ammonium sulfate. So remember, inner ions are going to pair up with outer ions. Okay, so our first one was calcium sulfate. Okay, and I'm going to go ahead and balance my compounds right now. calcium has a charge of +2, and then sulfate on the back of your periodic table. Okay, sulfate is a polyatomic, and it also has a charge of -2. Okay, so our charges are going to cancel each other out. We can leave it as calcium sulfate. Okay, and then we have ammonium chloride. So it's going to be NH4 and then Cl. Now ammonia is also a polyatomic. Ammonium has a charge of +1. Chlorine also has a charge of -1. So +1, -1, they're going to cancel each other out. There are no subscripts for these. Okay, so let's check. Calcium sulfate, is that soluble or insoluble? So sulfate is right here. So sulfate, calcium is not one of these exceptions, so that means sulfate is soluble. So we're going to have an aqueous compound. Okay, and then lastly we have ammonium chloride. So chlorine, okay, is ammonium one of the exceptions? No. So that means chlorine is going to stay soluble as well. Okay, because we have two aqueous compounds as our products, then that would mean no precipitate was formed, which would mean that no visible reaction was formed either. Okay, if you guys have any questions, please ask. Your test is going to be on Tuesday, so that's going to be coming up real quick. And then also on your homework, there was one thing that I noticed a few of you were asking me questions about, and it is this one right here. How do you separate what's what from what? How do you know what's your cation? How do you know what's your anion? Well, it's actually separated right here. Potassium is going to be your positive ion, and C2H3O2 is actually right here. It's acetate. Okay, so acetate has a -1 charge. Okay, but for some of you guys that were just asking on your homework problem, potassium is positive, and then C2H3O2 is actually acetate, which has a -1 charge. Okay, so when you're separating this for double replacement, that's how they would separate. Okay, so that concludes our notes for day 8, double replacement. If you guys have any questions, please ask.